In this video, we begin section 2.2, which discusses conditional statements. What is a conditional statement? A conditional statement is a statement that has the words if then. It's also known as an implication. Here's a quick outline of what we're going to be discussing in this section. In logic, when we make a logical deduction or inference, we reason from a hypothesis to a conclusion. A conditional statement is a statement of the form if P, then Q, and this is called a conditional statement. The part of the sentence where P is written is called the hypothesis. Q is called the conclusion. These statements are called conditional statements because the truth of the statement Q relies on the truth of the statement P. There are times when we write P arrow Q, just like this, or P with the two arrows Q to refer to the conditional statements. Let's practice by rewriting. If you study hard, then you will pass Math 265 using the arrow symbols. First, we're going to need to agree that the letter P represents you study hard, without the word if. The letter Q represents the second portion of the sentence. You will pass Math 265, again without the letters or the word then. Using this definition, we can rewrite if you study hard, then you will pass as P arrow Q. This is an example of what we call a conditional statement. The truth table for a conditional statement P implies Q is as follows. You'll notice that the truth table is only false in the case where P is true and the conclusion is false. The book gets into a little bit of a discussion on why this is true, and I would highly recommend you read that section. In terms of the order of operations, negations are always highest in priority, then ands and ors, and then finally the arrow is performed last. Let us show that P or Q implies R is equivalent to P implies R and Q implies R. Now, how can we do this? We can do this with a truth table. First, we need to begin by figuring out the size of the truth table. And in this case, the size of the truth table is going to be 8 rows. Why 8 rows? Because we have the letters P, Q, and R. There are 3 variables. Again, on the other side, there are letters P, R, Q, and R. So again, 3 different variables. So 2 to the power of 3 is going to be 8, and that means we need 8 rows. And using our order of operations, we know what needs to be placed in the columns of the table. So pause the video here and see if you can predict what the table in this problem looks like. Okay, I hope you got this table. So again, we start off by putting the PQR statements with their own truth and false possibilities. And again, since there are 8 rows, I'm going to have half of it be true and half of it be false. And similarly, I keep cutting by half every time and alternate between true and false. So that's how I build the first part of the table. Once the first part of the table is determined, I'm going to go through and figure out what to put in the next few columns. And in this case, I'm putting P or Q, which is a disjunction, and it's mostly true, except when both P and Q are themselves false. Now, the implication P or Q implies R is going to be true most of the time, except when the P or Q is true and the R itself is false. So this is basically this row, and also this row, and finally this row. Remember, the order here matters. We have to start with P or Q because that is the hypothesis, and we have to go to R. This is the reason why I drew my arrows going from right to left. Now, if we continue looking at P implies R, we notice that that one is again an implication. So again, it follows the same rule. True, false, true, false, true, 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 vacuously. QR, again with an implication, we fill the table up. And finally, what we have to do is look at the AND statement. P implies R and Q implies R. This is a conjunction, so we can use our knowledge from the last section to build the truth table there. And we notice that in this case, column number 5 and column number 8 have the same truth values in every row. So there's true here and true there, false here, false there, and so on and so forth until the end of the table. This implies that two statements are logically equivalent.